exactly the same, which can be problematic because sometimes one results are more interesting to us or more desirable. In this case, we want to say that 6 successful responses are better. For doing so, we can apply the weighting. Here in the formula 2, you can see for Shannon differential entropy, we multiply the FP, the distribution function by the weighting function Fi. And this function allows us to answer which outcomes are more desirable. The same can be done with weighted Fisher information, weighted Reni information, weighted Salis information. You can see the appropriate formulas here in the formula 3 to 5. And based on this idea, and actually in the Bayesian context, we have already been working on 6 different papers. The first one is the paper by Mark Elbert and Yuri Sukhov, context-sensitive hypothesis testing in exponential families. This paper refers to different development of mathematical framework for working with vast scope of problems, as well as medical and economic problems. And in papers 2 to 6, we are applying this mathematical apparatus. And in papers 2 to 4, we work with sequential decision-making problems. In papers 2 and 3, it is related to medical application and application to clinical trials. And in paper 4, we apply this search problem methodology to economic problems. And in papers 5 and 6, we work with conflicting expert opinions, which is not actually directly related to the search problems and weighted entropy, but is a good start for specific cases when we have conflicted expert opinions. And in these papers, we introduce a new prior distribution, which allows us to find the best alternative faster. I will quickly recap what was done in the paper published in Computational Science and Data Analysis, because the paper, which was recently published in the Biometrical Journal, is mainly based on this idea. So here, assume that we have and patients and X responses, and the prior distribution, prior information about each of the drugs that are studied during the clinical trials is given in form of beta distribution, and the posterior takes the form which is given in formula 6. And when we obtain new observations asymptotically, this posterior concentrates in the vicinity of certain point alpha. And after that, we can use the weighting function in beta form, and using this, we can calculate the exact and asymptotic criteria for choosing the next drug during the clinical trial. And the criteria can be either exact criteria, which will be denoted as a difference between the weighted entropy and the normal entropy, For the posterior function given before, which can be calculated for Renyi, Tsallis, Fisher, or Shannon's entropy, formulas 9 to 12. And also, we can use the leading term of this information gain, asymptotic expansion. And by doing this, we can derive the asymptotic criteria for each of the exact versions. And in this paper, we showed the formulas for the exact criteria in case of Renyi, Tsallis, and Fisher information. So for the Shannon's entropy, the results were already published by Pavel Mozgunov et al. And also, if we will apply the transformation, as I've said before, we can obtain the asymptotic formulas. For the case of Shannon and Fisher's entropy, for Renyi's and Tsallis entropy, it will be just, by definition, it will be just transformations of Shannon's entropy. Therefore, the criteria, the criteria for Shannon's entropy will be the same as for Tsallis and Fisher's entropy. So here, you can see that this criteria allows us to to achieve two goals, both exploration, because there is a term n plus beta plus 2 in the power 2 kappa minus 1 for Shannon's and 2 kappa for Fisher's, and exploitation, meaning that we want to find the treatment arm or the drug that is closer to our desired success probability gamma. And below in the slide, we see the quick recap of the algorithm that we are working with. We want to choose the next arm or the next drug that is given to a patient based on the minimization of this criteria, either asymptotic or the exact one. So here it is written in more detail for the exact entropy case, entropy criteria case. And after that, we define the metrics which will be used to differentiate the performance of different designs. And the ones that we're interested in is power proportion of correctly allocated patients. In formulas 19 and 20, we define the average percentage performance of a design. And in this plot, we are showing that indeed, using our method, using different criteria, asymptotic or exact, we can achieve the goal of finding different balances. In the top, we have the balances which are shifted towards power, and below, to the right of this plot, we have the designs with the balances shifted towards probability of correct allocation. So the best designs are the ones that are to the top and to the right of this plot. For the ones that are based on the asymptotic Shannon and asymptotic Fisher criteria are connected with the pointed line. Then we have compared it to the alternative design, dynamic programming design, which also allows us to find the different balances. And as you can see, our designs are still better in each case. In case of both designs that are shifted towards power and towards probability of correct allocation. Next, continuing working with this problem, we wanted to introduce randomization because in case of medical data analysis and clinical trials, it allows us to ensure that research preferences doesn't affect allocation of the patients, and also prevents any personal judgment being changing the course of the experiment. And in this case, we also generalize the case of binary endpoints to the case of multiple endpoints. Mathematically, not many things changed in this paper. We are still using the results which were proven in the previous theorem, in the previous paper, but here we extend the numerical analysis to the case of different number of treatment arms, and we investigate different scenarios with, again, the same metrics, which are power and probability of correct allocations. And here, again, we use different randomization methods. We compare under randomized procedure with a procedure based on naive randomization approach with allocation probability proportional to an inverse of informational criteria. We use block randomization method, which was presented in the paper by Wheeler and applied to Gittins index, and we made the same thing but with our entropy criteria. And next points 4 and 5 are related to randomization of penalty parameter kappa, which can only be applied to our method because this kappa penalty parameters is the parameter that intrinsically allows us to work with this balance, the balance between power and PCE. So in this paper, in this plot, there is average marginal power of checking the hypothesis that the null, that the first control arm and the second, the winning arm, are different. And the PCA, probability of correct allocation, across the winning scenarios. And here, you can see that our methods allow to find different balances, either shifted towards power, which are on the top, and shifted towards PCA, which are to the right of the plot. And by looking at this plot, we can see that our method allows to drastically increase power with a small difference in PCA for forward-looking procedures, and allows us to maintain more or less appropriate power at a level of 0.75 at least, but allows us to achieve much bigger probability of correct allocations than in case of fixed randomization methods. Now let's move on to the continuation of working with the storage problem. In this case, we are generalizing the idea of these search problems to the case of not binary, but multiple endpoints result. So for doing this, we are starting with defining the Dirichlet process. And the Dirichlet process, dp of H, where H is a base distribution, has two properties, two main properties, that for any finite partition Pi, and random realization of random variable X, X of this bi, the vector b1 up to x of bm follows the Dirichlet process, the Dirichlet distribution. And also, if E is a Dirichlet process with a base distribution H, if we will update the parameters, if we will add new observations, this process will still follow the Dirichlet distribution. The realizations of this process will still follow the Dirichlet distribution. And this property allows us to work again as a Bayesian setting, and Bayesian updating, usual Bayesian updating as we worked before. And we can write down the final posterior distribution for the case of multiple endpoint, which will be represented again as a Dirichlet distribution with updated parameters. Next, we have derived the weights function in the functional form adopted to the Dirichlet distribution, which can be seen in formula 23. And by working with this function, we have proven the theorem for the entropy gains for the Rényi, Shannon, and Salis entropies. And the idea of proving this theorem is exactly the same as before. We are just looking at the asymptotics of the weighted and non-weighted entropies and looking at the differences. Next, we apply look at the asymptotic expansion of this criteria for the Rényi case. If we will look at the first terms of this asymptotic expansion, we will obtain the asymptotic formula, which is represented here in the formula 26. And what is interesting here, a very intuitive result is, for example, if we will select 3 endpoints, here m equals to 3, and specify that gamma 1, gamma 2, and gamma 3 will be equal to 1, which are the probabilities for the desired probabilities for each of the outcomes. This formula will take the form given in formula 27, and it will be always positive and will have a unique minimum at 0 when our observed ratio will be equal to our desired ratios, desired success probabilities, Next, here I will quickly give the possible application of this method to economic problem. And here, for example, we can have 3 different strategies, investment strategies, or, for example, the strategy related to selling a good. Maybe if we have boxes of chocolate, and one can be sold in normal boxes, one can be sold in big packages, one can be sold in the beautiful big box that will be usually bought for giving a present, then we can say that each of these three possible outcomes will give us different revenues. Let's say B for bad will give us no revenue, normal or N will give us the good outcome of 10% revenue, and the great will give us an excellent result of $30 revenue. And for each of these cases, for each of these different strategies, we can specify the observed probabilities, RA, RB, and RC. And also we can write down the utility function in Cobb-Douglas form. And specify the initial budget and the price for investigating each of the strategies being $100. And say, given this budget, we can make 200 observations. And what should be the strategy of a firm? How should this firm choose the best strategy then? Using our approach, it should specify the desired probability distribution. Here it's gamma. And let's say that this decision maker, the firm, wants to have excellent results in 0.6 60% of cases, and he is okay with good outcomes in around approximately 40% of the cases, and he doesn't want bad results. So the strategy that he will choose is the one that will give the closest empirical distribution for the strategy. And to check that we are actually working with the desired distribution for each of the strategy or not, we can use Kolmogorov-Smirnov test. And using this, we will calculate power, which is our one goal. And the second goal will be maximizing utility or expected utility. And again, by tweaking the values of kappa, we can show different results, different balances between power and expected utility. So as you can see, the application of the weighted information measures, it can be done not only to in mathematical problems, but in any problems where we have two different goals, one of which is obtaining information and maximizing power. Finally, I will quickly recap what we have done regarding the problem of conflict expert opinions. And I will start with the idea of elicitation of expert opinions, which is the process of synthesis of any authority's opinions. And there are different methods for combining the expert opinions, which is either non-mathematical Delphi method or Bayesian or belief function approaches. In our case, we also work in Bayesian setting, but we propose to use the prior information, which accounts for the fact that we know that the experts are in conflict. And to do so, we need to consider a function f, which is defined in formula 28, which can be referred to as a generalization of the Dirichlet process to the case where we have this conflict. And it is based on the Zelbeck integral, which is defined in formula 29. And actually, f is a distribution function, and it's also known as a multivariate Zelbeck beta distribution. Here you can see if we will use this function as a so-called conflicted prior distribution, we can account for the fact that we know that our experts are in conflict because we have the last term, the absolute value of the difference between the zi and zj in the power of 2 gamma. And gamma will be the conflict parameter, degree of conflict parameter. Again, we can see that since it is a generalization of Dirichlet distribution, the posterior is also the conjugate posterior, so it also it will take the form of the same distribution with the updated parameters. And here we can see the moments of this distribution and how the conflict parameter gamma influences it. For it's the most interesting one, the most interesting plot here is how gamma affects the correlation between two opinions. If our gamma equals to 0, two opinions are not correlated. If gamma is greater than 0, then the correlation between the opinions is negative, and if it's positive, then correlation is also positive, and we can say that in this case there is not a conflict, but otherwise experts tend to agree with each other. In this paper, we are proving the properties of this distribution, and to do this, we need to consider a random variable that with the density given in the form shown below, before in the formula 29, and we need to normalize it first. It will be denoted as that tilde, and for this normalized variable, we have proven 3 theorems about the convergence of this normalized random variable to the standard normal distribution. Also, its differential entropy converges to the differential entropy of the standard normal distribution, and also the Kolbach-Leiber divergence between the density, the posterior density for this random variable and the density for the standard normal distribution equals asymptotically approaches 0. These are the mathematical results, and we are planning to apply them to the problem of prior data conflict. And in this case, first we need to define the prior data conflict. It can be referred to as a problem that occurs when the prior places most of its mass on parameter values that are not feasible in the light of data. And this prior data conflict was already discussed in case of in papers of Evans and Motional and the papers of Busquet. And what we want to do is we want to show that for some specific parameters, if we know that there is indeed conflict in expert opinions, our prior, which accounts for that, will allow us to achieve first, it will allow us to achieve the convergence to the truth faster, and also it will give us less of a prior data conflict. So here in Busquet paper, he has defined the data agreement criterion, which is defined as Kolbe-Kleber distribution between the Jeffreys prior, between the Jeffreys posterior and the prior that we're interested in. And it is divided over the Kolbe-Kleber distribution between the Jeffreys posterior and Jeffreys prior. And
Ksenia, тут Марк Яковлевич там некоторые вещи пишет, я прочел сейчас, видимо, сказать не может, что 21-я формула у вас якобы требует коррекции, там в знаменателе что-то. Он написал 4 минуты назад.
Окей, я поправлю, спасибо. Я думаю, что, если что, я думаю, там просто, да, какие-то с обозначениями проблемы. В целом все идейно правильно. Окей. Спасибо. Okay, I will continue. If data agreement criteria is less than 1, then prior data given the confidence region for data close enough, and the prior is in agreement with our data. And otherwise, we will have a conflict if the data agreement criterion is greater than 1. And we have derived the Kolbe-Kleber distribution for the Jeffreys posterior and our priors in case of the beta prior, and numerically derived the Kolbe-Kleber divergence for the case of the conflicted prior. Here you can see the data agreement criterion for beta distribution for different values of alpha and beta. And here we are adding the line for the conflicted prior distribution. And here you can see that indeed for these specific parameters, value of the parameters, we can say that our conflicted prior distribution allows us to get the wider area where we do not have the data and prior data conflict. So I think here we can stop. As you can see, the application of information theory and in particular, the context-dependent information measures is vast and can be applied not only to medicine and to economic problems, but also to any other problems where we are interested in obtaining a lot of information in the shortest amount of time. So thank you for the attention, and you're welcome to ask the question.
Thank you. Are there any questions?
Марк Яковлевич в чате писал какое-то замечание. Посмотрите, пожалуйста, Ксения.
Да, спасибо, это я уже увидела. Вроде новых кто не писал замечаний.
Ksenia, я по-русски, можно? У нас тут никого нет, иностранцев вроде бы.
Да, хорошо.
Ну вот она такая деятельность, она сильно прикладная все-таки. И вот, наверное, нужно иметь контакты с с какими-то людьми, которые могут это приложить где-то. Или же у вас все-таки оторвано от производителя, так скажем, какого-то?
Ну, вот то, что связано с медициной, это вот работы, которые мы еще совместно с Павлом Мозгуновым писали, там вот он, собственно, какие-то свои работы пишет по вот этой методологии, ну и наш в том числе, он там соавтором является, и, насколько я знаю, вот работает над тем, чтобы эти методы на самом деле были применимы в клинических испытаниях. Вот. Насчет экономической задачи, вот мы пока только теоретическую часть опубликовали. Ну, вот, может быть, если получится в хороший какой-нибудь журнал, связанный с поиском экономических политик, каких-нибудь в эту заметку отправить, то, может быть, кто-нибудь будет использовать эти методы там, в поиске инвестиционных стратегий оптимальных. Нет.
Понятно. Так, какие у нас вопросы еще есть? Ну вот еще Марк написал насчет, ну да, что журналы все, что статьи в журналах уровня А опубликованы. Понятно. Так. Ну, нет, если вопросов больше, тогда я хотел сказать, Марк Яковлевич что-нибудь добавить, может, хочет, но он добавить не может. Вот, тогда, значит, может, вы еще хотите какие-то направления будущих исследований сказать?
Ну, в целом, вот планируем дописать вот эти вот, подготовить окончательно вот эту статью про Data Agreement Criterion, пока что вот на ближайшие несколько месяцев. Вот заметку про экономическую с процессом Делихле. Ну вот, пока что это, вот дальше уже посмотрим.
Это
Скорее
вот в
всего.
рамках гранта вы этим занимаетесь, да? Правильно?
Да, это в рамках гранта. Раз.
Ясно. Что-то написал ваш коллега. План to revise all the background of the classical statistics. Ну, это амбициозный план, Марк Яковлевич, все пересмотреть. Это такие, мы знаем штуки. Вот. Понятно. Ну, хорошо. Тогда, значит, спасибо. Было полезно узнать, чем занимаетесь вы в рамках этого гранта. Вот. А Мозгунов там активно, да, работает? Он?
Нет, это только, ну, где? В Кембридже отдельно от нас активно, а в рамках гранта он
Нет,
уже
понятно. Понятно. Хорошо. Тогда, если нет вопросов, тогда будем на этом заканчивать. Вот Колесников, значит, не сумел, наверное, выйти сегодня. Может, у них с интернетом там что-то было, или, может, зума не было. Вот. Следующее у нас, Мария, вы напомните, что у нас там дальше? У нас отчеты аспирантов, что ли, да, будут?
Да, я сделала сегодня рассылку по аспирантам и частично по научным сотрудникам. Да, теперь отчеты остались.
25-го, да, они будут?
До конца пятницы следующей недели.
Угу. Сейчас. А 25-е это же не пятница.
А я не знаю, это какое число. Сейчас, секунду.
Ну, в общем, следующий 25-го меня уже, скорее всего, я не смогу подключиться тогда.
До
Колесников
20-го
там
я
будет.
писала, не ошибаюсь, да.
Ага. Хорошо. Ладно, тогда. Если у вас есть что-то, Ксения, со ссылкой на, ну, вот на наш лабораторный проект, то сейчас идет сбор как раз материал для отчета. Это и к вам, и к Марку Яковлевичу, что надо все собирать. Вот Мария сегодня уже начала всех опрашивать.
Туда мы это все внесем туда,
Да-да-да.
таблички. Все в
Ну
рамках.
вот, чтобы к нам не было претензий. Все, тогда спасибо. И на этом мы закончим тогда.
До свидания. Хорошего вечера.
Да,
Спасибо
взаимно.
за выступление.
Да,
Спасибо.
спасибо.